Okay, today we will start a new topic. I cannot say it's a steel structure topic. Also, I cannot say it's a concrete structure topic. It's composite structure. Composite structure means, just to remind you, during the last semester, we covered how to design concrete column. Do you remember that? If you have a column with the steel reinforcement, looks like this, or looks like this, whatever the shape, we can figure out the design compressive strength of this column. And I told you in the concrete course that the percentage of steel reinforcement inside this column between 1% to 8%. Do you remember that? If you go back to your notes, you will find how to design concrete column under the effect of axial load, P ultimate. And the design philosophy said P ultimate must be smaller than or equal phi Pn. In this semester, I covered how to design steel column. You have a column under the effect of P ultimate. We can figure out the design compressive strength of any column. Pn, if you remember, equal F critical time area gross. How to figure out the value of F critical? We have two cases based on KL divide R and its relation to 4.71, I believe, square root of E divide F yield. Based on this relationship, I can determine critical stress, multiply this critical stress by area gross. I can figure out the nominal strength, multiply it by phi. I can get the design compressive strength and make sure P ultimate is smaller than or equal phi Pn. That's right. So during the previous semester, we learned how to design column, concrete column. We have steel reinforcement embedded in concrete. And the percentage area reinforcement divide area gross of concrete between 1% to 8%. In this semester, we learned how to design steel column under the effect of axial compressive load. What will happen if you have this steel member embedded in concrete column beside reinforcement? Or if you have steel tube filled with concrete. My question is, do you think this column is concrete column, steel column, or composite column? I think this one will be composite because we have steel column combined with concrete column. That makes sense? So this week I will talk about composite columns. And it's very important to start the story from scratch. If you have concrete column alone, we have different technique in design. If you have a steel column alone, we have different technique. If you have composite column, I mean by composite means we have a steel column embedded in concrete, or we have steel tube filled with concrete. So we have composite column. Just to give you a hint, what is the meaning of composite structure? Composite structure means we have a structure is not concrete or is not steel. No, it's a combination between concrete and steel. So in structural engineer, composite construction exists when two different materials are bound together so strongly that they act together as a single unit. By the way, all of you understand or remember this information. Concrete is very strong in compression, but it's very weak in tension. That's right. And the steel will be excellent in tension and good in compression if you avoid buckling. So what will happen if we combine concrete and steel? Does that make sense? So it's a very strong to combine concrete in compression and put steel in tension to create a new structure called composite structure. Let's watch this video and see the construction of composite building. How it works. This video without sound. So just watch. Can you see? We have raft, foundation, and we have anchors, and here is the steel tube. Can you watch the connection? What's going on? Base of the column. And this column is not only for one floor or two floors, looks like 3 floors. We have crane lift the column to be fabricated at the position of the column. We will do the same for the other columns. We have many. Piece of cake, few seconds or few minutes, we are done with the whole columns for the whole building. That makes sense? Next step, we will have beams. Whatever the shape of the beam, it's not our point right now. So we have beams, and the edge beam will be attached to handrail. This is the idea. Guys, can you watch what's going on here? Do you remember the comparison between welded connection and the bolted connection? Bolted connection is piece of cake, few seconds and you are done. Can you see? Holes is ready, bolts are ready, just put your washers and nuts, and you are done with the connection. You don't need to weld or do anything. Here you go. We are done with the first beam. The same for the other beams. So we are right now connecting the grid of beams, steel beams, for the first floor. That makes sense? By the way, wait a moment, I'm sorry. The inside part is called core or shear walls. It's a huge amount of concrete. This one mainly to resist any lateral load. It will be around the elevators, stairs, all of this stuff, just to resist any lateral load, wind load or earthquake. This one. It's not our topic. Then we have corrugated steel sheet. Corrugated steel sheet. Will be supported between beams. And this sheet is bolted to the beams. That makes sense. We have, I will not say it's a reinforcement, but at least it's reinforcement mesh for shrinkage. Then we will pour concrete. So can you see? We have a steel beam, we have corrugated steel sheet, and we have concrete. All of them will be one unit. So we have composite structure. And the concrete is filling the columns. We are done with the first floor. So this first floor, I cannot say it's a concrete slab. I cannot say it's a steel floor, but I will say it's a composite floor. Composite floor. We will do the same for the second floor and the third floor. Then we will repeat one more time for new floor, new columns, new floors, and so on. Easy of construction, very fast, but we need professional techniques. It's a good question. I will answer this question shortly. Don't worry, Oliver. But did you watch the video? Did you understand what is the meaning of composite? So, if you look to the floor, we will have a steel beam. We will have steel beam. And we will have concrete slab. And we will have corrugated steel sheet. That means we don't need any formwork. We don't, no need. We don't need any formwork because the corrugated steel sheet will work as a permanent formwork. To make sure this beam is working with this slab as one unit, we need to add here shear connectors. Can you see these studs? These studs are welded on the top flange of the steel beam, and the concrete will be around these connectors. After hardening of concrete, we will have one unit. Cross section looks like this. Here is the concrete, here is the steel, here is the shear connectors. Any beam will be under the effect of this moment. This moment will do tension at the bottom, compression at the top. In between, we will have neutral axis. If you see here, concrete mainly under compression. Steel mainly under tension. We are good. This is the benefit of composite structure or composite construction. You are putting each material in the right place. Concrete is very strong in compression, put it in compression. Steel is very effective in tension, put it in tension. If you can do this, you are in the good track. Any questions so far? I will cover composite beam next week. But so far, any question? Do you have any question? So this topic will give you more experience about new construction. Okay. So composite beam, we have a steel beam, we have corrugated steel sheet, we have concrete, and we have reinforcement mesh. Mainly the reinforcement mesh only for shrinkage. We are worrying about shrinkage after the hardening of concrete. We need to avoid any cracks, any shrinkage crack on the concrete surface. So we add these rebars. For composite column, we have different shapes. The first one, we have a steel tube filled with concrete, and probably we are adding additional reinforcement. Probably yes or no for the additional reinforcement, but mainly we have a steel tube and this tube is filled with concrete. Probably yes or no, probably we have additional vertical longitudinal reinforcement, or the tube looks like rectangular shape filled with concrete and we have reinforcement. Sometimes we have concrete and we have steel column embedded in the concrete besides additional reinforcement. So if you look to any column, we will have area concrete, we will have area steel member, and we will have area reinforcement. Three areas: area for concrete, area for steel column, and the area for reinforcement. Let's start with the first one, this one. I will call it encased composite columns. Encased means we have steel column embedded inside concrete column. Besides, vertical reinforcement. That makes sense? Something looks like this. Regardless, the steps of solution or steps of design, because the steps of design is the donkey work, I would like to explain something for you. And please help me. Do you know why we put steel column inside concrete column? Can you think what is the main reason for this? Any answer? Why? Why I need to do this? Why I didn't use only steel column? Why I didn't use concrete column? Why I need to add both of them in one column? Any answer? Good answer, Oliver. It's a good reason. Okay, what else? I think there is one reason which is very important. It was the reason why the two high-rise building in New York collapsed in 2001, September 11. Okay, makes the whole column stronger. That makes sense also. Okay. There is one more reason. It's not our topic, but you can think about it. Temperature. Yes. Temperature. Temperature. Just a second. Fire protection. Steel is very sensitive to fire. Concrete is less. Steel is very sensitive. Concrete is less. So, for example, probably we can reach failure for steel after 30 minutes. I'm assuming 30-minute fire. For concrete, no. We can stay for 1 hour, 2 hours, or 3 hours. We have a building in my country. A few weeks ago, the fire continue. I think 48 hours. Continue firing. It was a big accident, but no collapse happened for concrete structure. 48 hours, but by the end they destroy the building because it does not will not work anymore. Anyway, but we didn't see any failure, any collapse during the fire. However, if you have a steel structure only, no, 30 minutes, 45 minutes maximum. Because steel is very sensitive to fire. So if you can put the steel column embedded in concrete, you are doing fire protection for the steel column. One more thing, guys, if you look to the stress strain curve for steel, this value is 50 psi in compression. If you look to stress strain curve for steel, for concrete, this value is 5 or 4 KSI maximum. Wow, 50 to 5, 10 times. So steel is 10 times stronger than concrete in compression. So if you are using concrete only, probably we will use 5 feet times 5 feet column. If you are using steel, I believe this 5 feet will be 0.5 feet times 0.5 feet steel column. This one will be steel. As you see, this one is 10 times the compressive strength of concrete. So the dimension of the concrete alone, divide it by 10, you can get the equivalent dimension of steel. But we have issue. If you are using this steel alone, 0.5 times 0.5, probably this column will be very long. So we can expect buckling. So we have issue right now. If you are using steel only, you will reduce the cross section to be smaller, but buckling will happen. If you didn't use steel and you are using concrete only, the concrete cross section will be very huge. So what do you think if we do combination? Because if the steel beam, the steel column is here, embedded in concrete, the concrete cross section will be bigger. So you are protecting this steel column from buckling. And you are adding protection against the fire. And I will not say we will have very thin column, but we will have a good cross section. It's not big and it's not small. That makes sense? That makes sense? Roberto, hot steel coming from fire. So if we have a fire, guys, what happened during the collapse of the commercial towers in New York in 2001? What happened? We have huge towers, and the plane hit the tower. My question is, do you think once the plane hit the tower, collapse happened, or there is a time around few minutes, 30 minutes, 45 minutes? Anybody remember what happened? Once the plane hit the tower, the collapse happened? Or the collapse happened after period of time? Yeah. So what happened during this hour? You need to ask yourself. The plane hits the tower, make huge fire at this location. This fire still heating the building. Every element in any building has fire resistance. This fire resistance probably 30 minutes, 45 minutes, 1 hour. After this time, collapse will happen. This is the case. When the plane hits the building, we have fire at this location. This fire was heating the element or the column of the building. After a period of time, whatever the design, 30 minutes, 45 minutes, 1 hour, collapse will start to happen. So the building or the two high-rise building did not collapse due to the hit of the plane. No, the plane make fire and the fire caused collapse. Okay, that makes sense? Anyway, so the first one or the first kind of column, composite column, is called encased composite column. We have concrete around steel column, and we have additional reinforcement, longitudinal bars. We have some limitations here. The cross-sectional area of the steel core, which is steel column, should be at least 1% of the total composite cross-section. And the concrete encasement of the steel core shall be reinforced with continuous longitudinal bars and lateral ties and spiral. we have here ties for shear, to resist shear and make confinement for the reinforcement. Anyway, the minimum reinforcement ratio for continuous longitudinal reinforcing rho shall be 0.004. This reinforcement to be considered in design should be at least 0.004. 0.004 means area. Reinforcement divide area concrete should be greater than or equal 0.004. Other than this, you can ignore the reinforcement. Anyway, so we need to design. Design means this column under the effect of P ultimate, and we need to make sure that the P ultimate is smaller than or equal phi Pn. How can I figure out the phi Pn? The design compressive strength phi Pn, where phi equal 0.75, we have two cases. This scenario or this scenario. Pn naught divide Pe smaller than or equal 2.25, or Pn naught divide Pe greater than 2.25. What is the value of Pn naught? Here is the equation. As I told you, we have area for steel column, we have area for reinforcement, we have area for concrete. If you multiply the area of steel column by F yield, the area of reinforcement by F yield of reinforcement, and the area concrete by 0.85 F prime C, and add all of them together, so this is the contribution for each part in the column. You can get Pn naught. So I can figure out the numerator. Pe where is Pe? There you go. I'm sorry. Pe is here. Elastic critical buckling by square EI effective divide KL square. So by square EI divide KL square. Guys, I believe we saw this equation before. K, do you remember the value of K? Sometimes the column is hinged. Sometimes the column is fixed, hinged. Sometimes the column is fixed. So this one, K equal 1, K equal 0.7, K equal 0.5, or fixed free, K equal 2. L, the length of the column. That makes sense. By square. EI, we will use EI effective because we have 3 parts. EI effective stiffness of composite section equal to this equation. E steel, I steel, plus 0.5 E steel, I reinforcement, plus C1 E concrete, I concrete. Most of the time, we can neglect this term for reinforcement. We can consider the part of steel column and the part for concrete. By the way, we will explain it in more details during the example. C1 equal to this equation, 0.1 plus 2 times area steel divide area concrete plus area steel, and should be smaller than 0.3. So right now, I can determine B naught, Bn naught, and Pe. So I can decide I will use this one or I will use this one. If you are using the first one, so the nominal strength will equal Pn naught times 0.658 to power this term. Or the second situation, Pn equal 0.877 Pe. Once you get the value of Pn, go ahead and multiply it by phi to figure out the design compressive strength. Once you figured out the design compressive strength, make a comparison with the applied ultimate. then you can say it's safe or unsafe. Keep in your mind, we have area concrete, we have area steel section, we have area reinforcement. Keep in your mind, we sometimes need e-concrete. Do you remember? Do you remember during the last semester? E-concrete, youngest models of concrete equal 57,000 square root F prime C PSI. If your units, US unit. Or the first equation if your unit is SI unit. We will use this one. And also keep in your mind steel youngest modulus for steel 29,000 KSI or 200,000 megapascal Newton by millimeter square. Most of the time we are using this one. If yield, guys, sometimes the yielding strength for a steel column is different than the yielding stress for reinforcement. So make sure we have F yield for steel section and we have F yield reinforcement for reinforcing bar. I concrete, I steel reinforcement. This one can be neglected. K effective length factor, L length of the column, F prime C compressive strength of concrete. Piece of cake. The design is easy. Just to follow the rules. Let's do this example. We have a column with length 14 feet. So L equal 14 feet. I think we need to convert it to inch. So 14 times 12, it will be 168 inch. Okay. This column is encased composite member illustrated in the shown figure. Determine if this column is adequate for the indicated dead and live load. This column, which is hinge, so K equal 1. And also this column under the effect of B dead load 260 and P live load 780. So I think P ultimate, which equal 1.2 dead plus 1.6 live equal 1.2 times 260, 1.6 times 780. This value will be 1,560 kip. So the life is easy. We need to make sure that the P ultimate is smaller than phi Pn. If you can do this, it's okay. The column is safe. If this not the case, the column will be unsafe. Let's start. What is the value of area steel? What is the value of area steel reinforcement? What is the value of area concrete? We have no, it's not missing. Can you see this information? W10 times 45. This steel column is made from W shape 10 times 45. So I'm gonna open my tables and look to this cross section 10 times 45. 10 times 45. 10 times 45. No, still down. 10. Yeah, here you go. 10 times 45. 10 times 45. Here you go. This one. The area for 10 times 45 is 13.3. 13.3 inches square. What is the value of area steel reinforcement? The steel reinforcement is number 8 bars. 1, 2, 3, 4, 5, 6, 7, 8. So we have 8 bars. Number 8. Anybody remember what was the area of number 8 bars? I don't have here any help.
Dr. Raymond Oliver said it's 0.79.
Okay, 0.79?
Yes, sir.
Thank you. So we have a table. This table can help you based on the size of the bar. I can figure out the area of this bar. So 0.79 times 8. So the total will be 6.32 inches square. So what is the area of concrete? This total length 24 inch. This total length 24 inch. But this is not concrete only. So we need to subtract area steel and subtract area steel reinforcement to get the pure concrete area. So 24 times 24 minus 13.3 minus 6.32. The area concrete will be 556.4 inches square. Does that make sense? So F yield equal 50 KSI ASTM A500. No, wait. For 500, I think it was in the first module in this course. Type of steel. Here you go. No, it's not available here. Anyway, so I will assume this type of steel A500 grade B. I'm gonna assume, I'm not sure about this value, but I will assume F yield will be 50 KSI. If you have your AISC manual, I have it, but on Canvas, not in my home right now. So you can open it and figure out this type of steel, what is the value of F yield. So I'm gonna assume it 50.
Dr. Raymond, I found it online. It says for round shapes, it's 46,000 PSI, and for the squares and rectangles, it's 50,000.
No, for W shape. How much?
So it's 50.
50, okay, so 50 will be good. That's fine. And F prime C for concrete, it's given 5 KSI. For F yield, for steel reinforcement, it's not given any information about steel reinforcement. No information is given. So you can assume the F yield for steel reinforcement with the same value, 50 or less, 40 or something like this. That's fine. So the first step, I'm trying to put my hands on all information which are given. So the length, the buckling factor, P ultimate, what is the area steel for steel column, what is the area steel reinforcement, and then what is the area concrete, what is the F yield for each part of the column. Then I will start. I will start with the first step. What is the value of Pn naught? Area steel times F yield. Area steel reinforcement times F yield steel reinforcement. 0.85 F prime C area concrete. Do you remember? PN note. F yield area steel. F yield steel reinforcement. 0.85 F prime C area concrete. Put your numbers. Put your numbers. Area steel. How much? There you go. 13.3. F yield 50. Area steel reinforcement 6.32. F yield 50. 0.85. F prime C 5. Area concrete how much? 556.4. Please make sure everything is good. So this area is still in inch square. This one in KSI, so I'm good. Inch square, KSI, I'm good. This one KSI, this one in inch square, we are good. Go ahead and find your number. So 13.3 times 50, 6.32 times 50, 0.85 times 5 times 556.4. This value will be 3,345.7 kip. What is the value of P buckling? Next step. Elastic critical buckling load by square EI effective divide KL square. By square EI effective. KL square. I think everything is known. K is 1. L, how much? 168 inch. By square is known. E for steel and EI, both of them one term, EI effective. So how can I figure out the value of EI effective? Here you go. EI effective equal E steel, I steel, plus 0.5 E steel, I steel reinforcement, plus C1 E concrete, I concrete. So EI effective equal E steel, I steel, 0.5 E steel, I steel reinforcement, plus C1 E concrete, I concrete. For your information, I can neglect this term. Why? The E steel value is very huge, but I steel is very small. So we can neglect this term. E steel 29,000 KSI. I steel, which is the smaller of IX or IY, smaller value. So you need to open your table one more time for W10 times 45. 10 times 45. This one. We have a value here for IX. How much? 248. And we have a value here for IY, 53.5. So I will use 53.5. That's right. 53.4. Plus C1 times E concrete, I concrete. 24 times 24 cube divide 12. For concrete, this cross section is 24 times 24. So the moment of inertia parallel times perpendicular cube over 12. E concrete equal 57,000 square root for 5,000. E concrete here 57,000 F prime C, but remember F prime C should be in PSI. PSI. And the given here, F prime C equal 5 KSI. So I multiplied it by 1,000 to be 5,000, should be in PSI. So 57,000 times square root of 5,000. So the E concrete value is 40, 30, 58. Looks like 4,030,508 PSI. So we have a mistake here. Anyway, keep going until we found something else. So the term for 0.5 E steel, I steel reinforcement is neglected. What about C1? C1 equal to 0.1 plus 2 time area steel divide area concrete. Let's do it here. 0.1 plus 2 time. What is the value of area steel? 13.3. Divide area concrete. What is the value of area concrete? 556.4 plus 13.3. What is the value? 13.3 divide 556.4 plus 13.3 times 2 plus 0.1. This value equal 0.14, which is smaller than 0.3. We are good. So C1 equal 0.14. Remember, be careful. 29,000 KSI. Moment of inertia, inch to power 4. C1 is a constant. This one, E concrete, PSI. Moment of inertia, inch to power 4. This one and this one are good. But this one, PSI, this one, KSI. You need to convert one to another. I think I will divide this value by 1,000 to be 4,030 KSI. So your value would be EI effective. It will be 1789520 kip. Kip inch square. Anyway, put this number. So guys, looks like I have a technical issue here, so I will restart my laptop. Just a second. Don't go away. So sorry guys. So your value for PE will be time pi square divide. So this value of PE will be 6,257 kip. And the P naught was 3,345.7. Why all of these calculations? Because we need to figure out what is the value of Pn naught divide Pe. Do you remember? If Bn naught divide Pe is smaller than or equal to 2.25, we are going to use this one. Let's see. So Pn naught, Be 6,257, Pn naught was 3,345. So your value will be 0.5. I think 0.5 is smaller than 2.25. So Pn equal this equation. Pn naught, then 0.658 to power Pn naught divide Pe. There you go. Put your numbers, and then you are done. Pn naught 3,345.658 to power this value, 0.5. So your value will be 2,674.4 kips. So the design compressive strength Phi Pn. What is the value of Phi? 0.75. Time Pn 2,674.4. Your value will be 2,005.8 kip. Can you remind me what was the value of P ultimate? P ultimate was how much? 1,560. I think we are safe. Does that make sense? So, how to design composite column? Just steps. Steps. You need to figure out these values. What is the area concrete? What is the area steel? What is the area steel reinforcement? E concrete, E steel. And you can follow these steps to use Pn equal to this case or this case. Once you figure out the value of Pn, multiply it by Phi to figure out the design compressive strength. Finally, you need to make a comparison between P ultimate and Phi Pn, and P ultimate must be smaller than or equal, at least equal. So by this example, for you as engineer, right now you have three options. You can design concrete column, go back to the first semester, the previous semester. You can design steel column, and right now you can design composite column.